In this problem, we turn our attention to abelian groups. We remember that abelian means commutative. And in this question, we're asked to consider in any abelian group, we don't know what the group is, that the subset H of x's with x equals x inverse is a subgroup. So in other words, the set of elements which are their own inverses. Well, for this kind of setup, the abelian hypothesis does not change what we have to check. So let's look at what we're dealing with again. We have neutral, we have inverses, and we have closure. For the neutral element, we have to ask ourselves, is the identity element in H? Well, in other words, is E equal to E inverse? I'm not sure that we've actually had cause to discuss this issue yet, but this is of course true. Because remember, what it means to be an inverse is that when you multiply into it, you get back E. But of course, E times E is E. So the equation E times E equals E is basically a proof that E is E inverse, right? I could put an inverse sign here and it would still be correct. Similarly with over here. A little bit weird to think about, but true. Maybe it's worth it for you to pause the video and take a moment and just convince yourself that that's correct. Inverses, on the other hand, follows from the theorem that we saw that any element inverse is the element again. So in other words, if I plug x inverse in where x goes, I would be needing to check that x inverse equals x inverse. But x inverse equals x. And so that's the same thing as just switching these two things. And we know that the equal sign is symmetric. So of course that's true. For closure, we have to see why if x and y are in H, then xy is also in H. And this actually follows from something from the homework. Let's spell it out. If x is equal to x inverse and y is equal to y inverse, is xy inverse equal to xy? That's the question. Well, what we know is that from our shoes and socks lemma, this will be equal to y inverse x inverse. And now from assumption, each of these is individually y and x because x and y are in our set H, so they become equal to themselves. Lastly, since the group is abelian, we can reverse the order and get xy. xy inverse equals xy. We declare victory.